it's time to revisit our old friend that we saw in section 10.1, which is geometric sequences. Now remember, geometric sequences, in case you've forgotten the definition, means that you're multiplying when you're making a recursive formula. So in the recurrence relation, you're multiplying or dividing, right? Because division is just multiplication by a fraction, by the same number. Which means, based on our algebra skills, that in the explicit relationship, in explicit formula, I should have said recurrence relation here. We learn in algebra 2 that when you're multiplying by the same amount every time, that would be that same number, which we'll call r, will be the base of our exponent of an exponential formula, I should say. All right, so let's compare and contrast some behaviors here and see if we can come up with some ideas. Okay, so if I have 0.75 to the end, this is what the graph looks like. I can show us the table because I have this, of course, built in Desmos. My life would not be complete without more Desmos. All right, so if I take 0.75 to the end, you can see that those numbers are shrinking, right? That those values are getting smaller and smaller and smaller. Okay, so then that means that it is monotonic, right? It is decreasing. Is it bounded? Yes, it is bounded. All right, it's bounded on the bottom by 0, which is the only part that we care about, since it's decreasing. And therefore it's convergent, right? This converges to 0. You can see that sequence is getting closer and closer and closer to 0. All right, now what about negative 0.75 to the end? To the end, excuse me, not to the end. So again, let's look at it in Desmos. So I've got this turned off, and I'll turn this one on. And there it is. Now, it is also shrinking, right, in size, but it is not monotonic because it is bouncing between positive and negative values. Okay, so that would mean it is not monotonic. So let me say that. Monotonic is a big no. Bounded, that's a tougher call. In the end, I would say yes, it is bounded, because we can get as close as we want underneath some value. I mean, we can tell that we're approaching 0. I mean, that's kind of obvious. It's converging to 0. So, I mean, I can get the convergence more easily than I can get the bounded. It's bounded above by whatever this number is and below by whatever that number is. I mean, it never gets above or below those values. And honestly, as we head towards infinity, it's getting closer and closer to 0. So you could say it's as close to 0 as you like. So we will say it is bounded, although bounding in general doesn't matter so much for an alternating series, but we'll just say yes for our purposes. It's kind of trivially bounded on the left end, but in the long run over here on the right, it's also bounded. There's some number above and below that it won't get up past, and that's fine too. So it's a little trivial, but sure. It's fine. Or it's not trivial. It's getting into weedier definitions of bounding than I want to deal with right now. All right, so I guess I'll just leave it at that. I'll just leave it as yes, and we'll just call it a day. All right, now what about this one? Well, that's not bounded. That's going to infinity, right? The exact opposite of this. So this is not bounded, but it is monotonic. It is increasing. So monotonic, which is a big fat yes. Bounded is a big fat no. And therefore it's not converging, right? It diverges. This one actually diverges to infinity and beyond. Sorry, can't help myself. This one is also divergent. You can see it's bouncing between positive and negative infinity. Again, not bounded, right? So bounded is big no. Convergent is no. Bounded is no. Monotonic is no. This one's a no, no, no. just to make it consistent, I actually put converges on all of these, and then I just said no for these bottom two. So this one's yes, yes, yes. This one's no, yes, yes. Yes, no, no, and no, no, no. None of these. Now, why did I put all four of these examples together? Well, because they're all geometric sequences. All four of these are taking a number, r, and raising it to a power, which leads us to a theorem, a very important theorem about geometric sequences. Let's look at this theorem in a different light. Let's look at it with Desmos, which of course I have it built right here. So I'm taking r and I'm raising it to a power. It can be technically r to the n1. There's no relevance here for n5. And I want us to look at this graph. Don't worry about r equals. That's just irrelevant. Okay. So then look at what happens if I change this. I'm going to add in a few more dots here just so we can see more. Okay, so if I make it go down to, between -1 and +1. So here's a negative, or there was a negative value. There's a negative value. Oh, let me zoom in so we can really see this. So I don't mind the x's, but I do mind the y's. So I'm going to go like that. So that way we can see a little bit better. Here. There we go. Now we're cooking. Okay, so see those dots? So for a negative r value, it's bouncing, right? Positive, negative, but it's converging. And then over here, positive r value, it's converging. And then if I let r get large, so let me let r turn into 1. Oh, I got to zoom out so you can see it. Right? Because 1 to a power is 1. So when you let r equals 1, it's just 1, 1, 1, 1, 1, 1, 1 all the way along. And then if I let r get larger than 1, oh, you won't be able to see it. Now my y scale is not helping me at all here. Hold on. That's what it does. What if I let r be -1.2? Let me go this way. Oop, I went too far. There you go. You see, it's the same as it was when it was 1.2. It's the same thing, except it's bouncing. Half the dots go below and half the dots go above because the even powers are positive and the negative powers are negative. Or I mean, the odd powers are negative. All right, now what if I let r get larger? So if I say, sure, -1.2, I don't care. If I get it larger in terms of negative, I'm going to slay this slider bar down. It's so large that it's literally off the screen already, right? Look, it's at 30 and then 90 and 244. Look at those numbers. Similarly, if I let r go to +2.5, it's the same numbers, but they're all positive, right? So what are we learning? Well, if r is small, say like a decimal between, oh, I don't know, -1 and 1, in here, it converges. The sequence converges. Once I let r get larger than that, now r equals 1 is just 1, 1, 1. R equals -1, let me get there, would be -1, +1, -1, +1, -1, +1. So those ones are kind of special, right? But once r is anything larger than that, then whoa, you got trouble. -1 actually is so interesting. We're gonna look at that one some more. So let me put it back at -1. And let me zoom in again. And we'll talk about that. All right, so we've learned some valuable lessons that we want to put into this theorem. Okay, so number 1, if r is between -1 and 1, that's what happens when the absolute value of r, right here, absolute value of r is less than 1. That means that -1 is less than r, which is less than 1. It's from here to here. It's this zone in here that's being shaded. So if you're in there from -1, you will converge to 0, period. If you are 1, specifically this single value, 1, if r is 1, it will converge to 1. The sequence will converge. If r is any other number, if r is either greater than 1, which is this zone over here, or less than or equal to -1, right? Because -1 is kind of a weird case. If r is any of these values, it will also diverge, including at -1. Because -1 doesn't get anywhere good. 1 is kind of easy because 1 is always just 1, 1, 1, 1, 1. But -1 causes that hopping thing, which we said in a previous problem is divergent. It's not getting to any specific value. All right, so this is a very important theorem. We're going to want to keep it in mind. This is a big deal, right? So geometric sequences, which occur when you multiply or divide, because realize that when you're multiplying by a fraction, you're technically dividing, right? So when you multiply or divide, if it's the ratio that you are multiplying by, r, is between -1 and 1, right, then you will converge to 0. That sequence will converge to 0. If it is 1 specifically, it will converge to 1. Any other number from -1 over and greater than 1, it will diverge. So convergent in here, but not at that spot. Divergent over here and divergent over here.